So on example 8, we have actually the one-to-one setup, right? They do the ln on both sides. So we can set these two things equal to each other. So I can bring out the square root of x plus 2 equal to x due to the one-to-one property. So you're going to square both sides. I get x plus 2 is equal to x squared. Now we're not doing chapter 2 here, but you're running into a quadratic, so that goes all the way back to chapter 2. So I would bring everything over to here because I like my x squared to be positive, so I'm going to bring everything to this side. You have x squared minus x minus 2. How does that factor? X minus 2, x plus 1 would be the two factors. So when you set each of those factors equal to 0, you get answers that are like 2 and negative 1. Now, was this x squared right here in the problem? We created that, right? And x squared allows for positive or negative numbers to work. So we definitely want to take that answer and plug it back in. The 2 will go here, and 2 plus 2 is 4, so the square root of 4 is 2. And so what I end up with is ln of 2 equals ln of 2. So this one works. 2 will work. Now when I plug in negative 1, what's going to happen? Negative 1 plus 2 is 1. So I can actually plug in, just because it's negative doesn't mean it won't work. Negative 1 plus 2 is square root of 1, which is the natural log of 1. But what's happening over here?
So negative 1 doesn't work.
So it isn't that a negative doesn't always work or something, so be careful, plug it in. It's because logarithm of a negative won't work. So get rid of it. That's called an extraneous solution. All right, I'm going to pause it. For example 9, you're going to squish it together and then see what happens. So go ahead and work on that. So if you squish them together, you're going to write a logarithm. When you combine them, it's one logarithm. You're subtracting, so that x goes over x minus 3. And again, without the base sitting there, a lot of students stop the problem, but this is a base 10. So we need to rewrite it. It'll be 10 to the first power is x over x minus 3. So if you want to, this is a whole number. If it makes you feel better, like make it 10 over 1. And then you can cross multiply or whatever you're going to do. But I would multiply by x minus 3 over here, get rid of it there and there. Little chunga chunga. This is x minus 3. So when you multiply the 10, you have 10x minus 30 is equal to x. Probably the easiest is to subtract 10x. Divide by negative 9.
Cats, wouldn't it be 10 to the power of 0 to equal 1?
What?
No, hang on. So divide both those by 3, you get 10 thirds. Again, we're starting off with the logarithmic problem. The variable is inside the logarithm. So you have to divide by 2 to get it by itself. And you can write 2.5 or 5 halves. It's the same thing. Now, what do we do? Again, it's really base 10 here.
That it is.
So it'll be 10 to the 5 halves power is equal to x.
Can we leave it like that?
You can certainly leave it like that. If you type in 10 raised to the 2.5 power, 316.2278.
7766
What was it? 0.772278. Either one is fine. It should start to feel like almost every problem is the same. It's like you either get that logarithm by itself and then rewrite it as an exponential, get the exponential base by itself, rewrite it as a logarithm. What are we doing here? Divide by 2. Add 1. Now I do get a lot of people that say this is 1/2 because what they're thinking is 3 is half of 6 or something. But it's an exponent, so that doesn't work. 3 is not a nice base. It doesn't have a button on the calculator, so we might as well go right to the ln on both sides. That allows the x to come down in front. Divide by the ln of 3. And a lot of you might start to get used to this. This is a base that's not on our calculator. You can go right to the base change here. And if you want the approximation, go right ahead. Exponential logarithmic unit. You're always going to have a couple application problems where the variables are what you're solving for. So we're going to invest $5,000. We want to let it sit until it's $350 so that we can retire in 30 years. At what continuous compounded interest rate would you need to invest the money to reach your goal? So first of all, once I've read continuous in the problem, I know I'm doing the PERT formula.
Hurt.
So I'm going to start with $5,000. I do not know the R. T is going to be 30, and I want to end up with $350,000. It's exactly now like the problems that we've been doing. I have to get the base by itself. So 350,000, oops, not 120, divided by 5,000, 70. Now this is already a base E exponential, so what logarithm should we apply? Yeah, I mean you can apply any logarithm you want, but if you apply the ln, when the R30 comes down in front, ln of E is 1, so I don't need to write times 1. Then I just divide by 30. Now, this is an application problem. Nobody knows what ln of 70 divided by 30 is. If somebody said, you know, you walk into a bank and they say ln of 70 divided by 30 is your interest rate, you probably sock them in the neck and say, I don't know what that is, right? In application problems, you must give me the approximation. Also, what is R in the problem? It's an interest rate, not the decimal. So you're doing
1.
ln of 70 divided by 30. That's the decimal in the problem. So if I multiply that by 100,
By 0.
100. The bank is offering me about 14.16%. Or I need to make sure my investment stays close to 14.16% to have that amount of money at the end. You have deposited $2,000 in an account paying 4.25% interest, compounded continuously again. So we're going to use that PERT formula. How long will it take your money to double? T. We're going to look for T in this problem. Now, what happens is a lot of times students write the stuff out. They go, okay, I have $2,000. E to the point 0.425 times T. And they go, well, I don't know how much money I have in the account. But doubling is multiplied by 2. So I'm going to have $4,000 at the end of this. Now in any doubling or tripling problem, when you get the exponent by itself, no matter where you start and where you end up. A doubling problem will have a 2 on this side. A tripling problem would have a 3, and so on. Okay, well, what's the exponential base? Exponential base is e. So we're going to apply an ln on both sides. The exponent comes down in front, same as it's been doing. ln of e is 1, so that's all we have. Divide by 0.0425. Same thing. If you have a little brother or sister that walks around the house saying, I'm the natural log of 2 divided by 0.0425, you're going to do what? Sock him in the neck. Right? That doesn't make sense to anybody. Figure it out for them. Let them know. So now we have the ln of 2, thank you, divided by 0.0425, and it's going to take approximately 16.3 years. 16.3 years. And we're done.